Hello everyone, I am Afsana and Jeny. Today I am going to present our accepted paper. The paper ID is 52 and the paper title is Residual Learning and Filtering Networks for End-to-End Lossless Video Compression, and here are the authors of my paper. This is the outline of my today's presentation. Let's talk about the motivation of our paper and also the limitation of the previous paper. Actually, there are some traditional popular video compression techniques like is 0.264, is 0.265, and VVC. Actually, they are not end-to-end network, and also they use the hand-encrypted features. So that is diminish the quality and user experience as well. There are some methods used DNN, I mean deep neural network nowadays, and that is already published. But actually, the deep neural network architectures are struggling to make the temporal consistency challenges unique to the videos. Therefore, to ensure video compression system more effectively, we require some. We need to consider some multiple components on the multiple components. For example, the optimization of the entire system, precise motion vector information, and striking the right balance between the rate and distortion. And another most mandatory component in the video compression is the deep autoencoder structure, which is recently made by the transformers. But you know the transformer is really very much computationally expensive and memory constraints as well. On the other hand, if we use a simpler network, that might lead to compression inaccuracies, and especially in the low bitrate scenarios for post quantization. So with the observed drawbacks in the existing methods, we just try to design a lightweight end-to-end powerful compression system that boosts the video compression performance and diminishes the compression errors for final optimal visual experience of the reconstructed frame. These are the contributions of our paper. First of all, we just introduce an end-to-end architecture of video compression system that including different type of components. For example, the motion estimation, motion compression, motion compensation, residual compression, and entropy coding that is based on the rate-distortion trade-off. Then we proposed compression network that is we called autoencoders, and employing residual blocks, skip connections to extract high level and high semantic features from different layers. Then we proposed two filtering networks, that is MVF, we called motion vector filtering and residual filtering, that are proposed to mitigate the compression artifacts in the reconstructed frames, and these networks improve the visual quality of the reconstructed frame as well. Then we just use deep rectifiers, PRELU, are employed in the motion compensation and filtering networks to improve computational efficiency by minimizing the training parameters. And we also introduce some multiple residual blocks in the predictor frame to make it more smoother. So this is the proposed architecture of our paper. First of all, we just sent the current frame FT and the previous reference frame FT-1 to the optical flow network to get OT, and then we just send this OT value to the MVC motion vector compression network to get the raw values OT. And here for this quantization errors, I mean this autoencoder architecture, there are some quantization procedures. So after that we got quantization errors. So for removing these artifacts, we just proposed MVF network, motion vector filtering network, to get the OT, and this OT we just send to MCDR network to get the predicted frame. This MCDR network we just on the previous component of MCDR network we just modified a lot, and finally from this MCDR network we get the predicted frame. After that we just send this frame into the RCA block. This is a residual component, residual compression network, and here we just proposed RF network because this RC component, like the MVC component, here also there are some quantization procedures. So for this one actually our predicted frame also shows some compression errors. That's why we just use residual filtering. We just propose residual filtering network to reduce these compression errors. After that, this RT and this predicted frame FT-1 we just add it and get the final reconstructed frame. Here we use decoder buffer online, and this one actually we used to the reference frames, to fine tune the reference frame again and again for making the clear reconstructed frame. The output will be more good and smoother. That's why we use this DFB, online buffer. Okay, this is the proposed components of our network. We use different components. For example, motion estimation. This component actually captures motion information between video frames for efficient compression. Then MVCN, that is motion vector compression network, encodes motion vectors leveraging deep learning for improved efficiency. Then motion vector filtering network that refines motion vectors to reduce compression errors and enhance frame prediction quality. Then motion compensation network that works a frame based on motion information, enhancing compression efficiency by addressing temporal redundancies. Then we used residual compression and filtering network. This component actually processes and refines the differences between original and predicted frames, and also improving the overall final reconstructed frame quality. After that, we use the loss function and entropy coding that optimizes the trade-off between compression efficiency and video quality, and accurately estimate bitrate blocks as well. So this is the experimental details for showing the effectiveness of our proposed model. We used multiple dataset. For example, for the training dataset, we used Vimo 90K, and here almost 90K video clips, and each video clip the resolution is 448 by 256 pixels. We use HVC different type of sequences. For example, class B, C, and D. There are the combination of high resolution frames and also the low resolution frames. Then we used MCL JCB dataset. That is also high resolutions, and UVC dataset that is also high resolution images. Then BTL dataset, these are low resolution images. So we just try to combine both high resolution and low resolution to show the effectiveness of our proposed model. And here are the implementation evaluation details. For the evaluation matrix, we used PSNR and MSSSIM. We also use a VDVR evaluation matrix, that is we just expressed in BPP. And for this BDPR evaluation matrix, we just used because it shows better compression efficiency results. And we use different type of GOP, that is group of pictures, to show the effectiveness of our proposed method. For example, for the UVC, MCL, JCB, and BTL dataset, we use group of picture 12, and for the SVC sequences, we use 10. So for the fair comparison, we just modified something and with the traditional method and also deep learning methods, and we show it in ablation study. And here is the evaluation of the MSSSIM. You can see that the dot blue line that represents our work. So you can see that our model shows sometimes state of the art performance and sometimes second highest performance, but it shows a very much competitive performance with the traditional methods and also new recent deep learning methods. If you just notice this one. And here is the evaluation of the PSNR, and here also you can see that our model sometimes shows the state of the art performance, but sometimes shows second highest performance. For example, in HBC class D dataset and BTL dataset, actually BTL dataset is very much low resolution, that's why it shows a little bit less performance, but definitely it shows demonstrates a competitive performance with traditional methods and also recent deep learning methods. And here is the BDBR evaluation. In the BDBR evaluation, you can see that our model also shows a very much good performance. Here, negative performance shows a very much good compression efficiency. And here is the results of the final reconstructed frame. You can see that this left portion, this is the ground truth, and this is our final reconstructed frame. It's almost similar if you see the MSSSIM, and this result, the right portion shows the proposed our proposed filtering networks. If you see this portion, that is the ground truth, and second rows, it is without MBF and RF network. If you see that this is not clear and even blurry, but when you use our proposed MBF and also RF network, it becomes more clear and more smoother. And this is the ablation study for our proposed components. You can see that if we don't use a component of our proposed component, it shows less accuracy, but when we use all of the components together, it shows the highest performance, almost more than 35. It is the PSN evaluation 35 decibel. And this one, the evaluation of the proposed autoencoder. We just kept the autoencoder last feature vector size is 1024, because if we use 2048 it becomes computationally more expensive, but the performance doesn't improve very well. That's why we just decided to keep up to 1024 a feature space in the last layer of the autoencoder. And as a I just mentioned all of the contributions previously. So the future work, we just try to improve the, try to propose an entropy model to further optimize compression, and also our aim is to show the more effective performance, video compression performance, and overall efficiency in the future. So that's it. Thank you very much for listening.